Welcome everyone to this exciting journey through Einstein's groundbreaking theories. Today we'll explore how Einstein revolutionized our understanding of space and time, delve into the possibilities of time travel, and discover how modern technologies like quantum computing and artificial intelligence are helping us understand these complex concepts. We'll keep everything simple and accessible, using everyday analogies to make these fascinating ideas clear to everyone. Einstein's theory of relativity fundamentally transformed our understanding of the universe. Before Einstein, space and time were seen as separate, absolute concepts. His work showed they're interconnected and relative. This isn't just theoretical. It has practical applications. GPS satellites must account for relativistic effects to maintain accuracy. Without these corrections, GPS would be off by miles within hours. Relativity also led to discoveries of black holes, gravitational waves, and helped us understand the expanding universe. It bridges the gap between our everyday experience and the most extreme cosmic phenomena. Think of space-time like a giant trampoline stretched tight. When you place a heavy bowling ball in the center, it creates a dip or curve in the fabric. This is exactly how Einstein described space-time. Massive objects like the sun create curves in the fabric of space and time itself. Everything in the universe, from light rays to planets, must follow these curves as they move through space. This simple analogy helps us understand one of the most profound discoveries in physics without needing complex mathematics. Einstein's special relativity, published in 1905, was a revolutionary breakthrough that fundamentally changed how we understand space and time. The theory establishes that the laws of physics work the same way for all observers moving at constant velocities, meaning there's no absolute reference frame in the universe. Most remarkably, it shows that the speed of light is constant for everyone, regardless of how fast they're moving. This leads to the counterintuitive conclusion that time and distance are not fixed, but depend on your relative motion, laying the groundwork for modern physics. The speed of light represents one of the most fundamental constants in physics, acting as nature's ultimate speed limit. At nearly 300,000 kilometers per second, light sets an absolute barrier that nothing in the universe can exceed. This isn't just a theoretical concept. It has profound implications for space travel, communication, and our understanding of time itself. When Einstein discovered this limit, he revealed that it fundamentally shapes what's possible in our universe, including the mechanics of time travel and the behavior of matter and energy at extreme speeds. Time dilation is one of Einstein's most fascinating discoveries. As objects move faster, time literally slows down relative to a stationary observer. This isn't science fiction. It's been proven through experiments with atomic clocks on jets and observations of fast-moving particles. While the effect is negligible in everyday life, it becomes significant at high speeds and is crucial for space travel and GPS satellites. This slide illustrates Einstein's time dilation through the famous twin paradox thought experiment. When one twin travels at high speeds through space, they experience time more slowly relative to their Earth-bound sibling. This isn't science fiction, it's measurable reality. Astronauts on the International Space Station actually age slightly slower than people on Earth, though the difference is only microseconds due to their relatively modest speeds compared to light. Einstein's most famous equation, E=mc² shows us that mass and energy are two forms of the same thing. This revolutionary idea means that even a tiny amount of matter contains enormous amounts of energy. This principle explains how atomic bombs work and how nuclear power plants generate electricity. It also explains how the sun and all stars shine by converting small amounts of hydrogen into energy through nuclear fusion. This discovery fundamentally changed our understanding of physics and led to both peaceful uses like nuclear medicine and power generation, as well as the development of nuclear weapons. The equation shows that the speed of light squared acts as a conversion factor between mass and energy. General relativity, published by Einstein in 1915, revolutionized our understanding of gravity. Unlike Newton's view of gravity as a pulling force, Einstein showed that massive objects actually curve the fabric of spacetime itself. Think of it like placing a bowling ball on a stretched rubber sheet. It creates a depression that causes smaller objects to roll toward it. The more massive the object, the deeper the curve. This elegant theory explains why planets orbit the sun, how black holes form, and why light from distant stars bends when passing near massive objects like our sun. This slide explains gravitational time dilation, one of Einstein's most remarkable predictions. The concept shows that time is not absolute, but relative to gravitational fields. Near Earth's surface, where gravity is stronger, time moves slightly slower compared to higher altitudes where gravity is weaker. This effect is measurable and has practical applications. GPS satellites orbiting Earth experience this time difference and must constantly adjust their clocks to maintain accuracy. Without these corrections, GPS would become unreliable within hours. The effect becomes more dramatic near extremely massive objects like black holes, where time can slow to a crawl relative to distant observers. Black holes represent the most extreme example of Einstein's general relativity in action. Their immense gravity warps space-time so severely that time itself behaves in extraordinary ways. At the event horizon, time dilation becomes so extreme that time appears to stop completely from an outside observer's perspective. This creates a fascinating paradox, where someone falling into a black hole would appear frozen at the edge to outside observers, even though they continue falling from their own reference frame. Inside the event horizon, our current understanding of physics reaches its limits, as the laws of relativity and quantum mechanics clash in ways we don't fully comprehend yet. Wormholes are fascinating theoretical constructs that emerge from Einstein's general relativity equations. Think of them as cosmic shortcuts, like folding a piece of paper and poking a hole through it to connect two distant points. While mathematically possible, we have no evidence they actually exist in nature. The concept has captured imaginations in science fiction, but real wormholes would likely be unstable and collapse instantly. Even if they existed, traversing one would require exotic matter with negative energy density to keep it open. Despite being purely theoretical, wormholes help scientists explore the boundaries of physics and spacetime geometry. While Einstein's field equations don't explicitly forbid time travel, they reveal the enormous challenges involved. The energy requirements would be astronomical, potentially requiring the mass energy of entire stars. Additionally, we would need exotic matter with negative energy density, which has never been observed. Scientists continue studying these theoretical possibilities through mathematical models and thought experiments, but they remain highly skeptical about practical time travel ever becoming reality. Time travel paradoxes represent some of the most fascinating puzzles in physics. The grandfather paradox asks what would happen if you went back in time and prevented your own grandparents from meeting. Would you cease to exist? This creates a logical contradiction. Causality issues arise when we consider events that could prevent their own occurrence. While no definitive solutions exist, some physicists propose parallel universe theories where changes create alternate timelines rather than altering our original timeline. These paradoxes raise profound questions about fate, free will, and the fundamental nature of time itself. This slide distinguishes between Hollywood's portrayal of physics and actual scientific reality. While movies like Back to the Future and Interstellar make time travel look easy, real physics shows we haven't developed practical time machines or stable wormholes. However, phenomena like black holes and time dilation from relativity theory are supported by extensive observational evidence. Science fiction serves an important role by inspiring scientists to ask new questions and explore creative solutions to complex problems, even if the depicted technologies remain beyond our current capabilities. This slide introduces one of physics' greatest challenges, reconciling quantum mechanics with relativity. Quantum mechanics beautifully describes the behavior of atoms, electrons, and subatomic particles at the smallest scales. Meanwhile, Einstein's relativity theories perfectly explain gravity, spacetime, and cosmic phenomena at the largest scales. However, These two pillars of modern physics use different mathematical frameworks and make different assumptions about reality. When physicists try to apply both theories to extreme conditions like black holes or the first moments after the Big Bang, the equations break down. This incompatibility drives the ongoing quest for a unified theory of everything that could merge quantum mechanics and relativity into a single, coherent framework. Quantum computing represents a revolutionary leap in computational power that's particularly relevant to understanding Einstein's theories. Unlike traditional computers that use bits existing as either 0 or 1, quantum computers use qubits that can exist in multiple states simultaneously through quantum superposition. This unique capability allows them to simulate the incredibly complex physics of spacetime, black holes, and other relativistic phenomena that would be impossible to model accurately with classical computers. Scientists are using quantum computers to test theoretical predictions about time travel, wormholes, and the fundamental nature of reality itself. Artificial intelligence is revolutionizing physics research by handling enormous amounts of cosmic data that would take humans years to process. AI systems can analyze information from black holes, distant galaxies, and gravitational wave detectors, identifying patterns and anomalies that might escape human observation. These systems excel at modeling complex phenomena like wormholes and extreme spacetime conditions, performing calculations in minutes that would traditionally require months or years. Most importantly, AI accelerates scientific discovery by suggesting new experimental approaches and making predictions based on vast datasets, helping physicists explore the mysteries of relativity and quantum mechanics more efficiently than ever before. This slide highlights the exciting frontier of modern physics research. Scientists are working toward a unified theory that combines Einstein's relativity with quantum mechanics, which has been one of physics' greatest challenges. They're also investigating mysterious cosmic phenomena like black holes, dark matter, and dark energy that make up most of our universe, but remain poorly understood. Perhaps most exciting is how artificial intelligence and quantum computers are revolutionizing our ability to model complex cosmic scenarios and even explore theoretical possibilities like time travel that were once purely science fiction. This concluding slide wraps up our journey through Einstein's revolutionary theories. Einstein didn't just give us equations. He fundamentally changed how we see space, time, and reality itself. His work opened doors to technologies we use today and fueled our imagination about time travel possibilities. Modern quantum computing and artificial intelligence are building on his foundation, helping us explore even deeper cosmic mysteries. The key message is that science is an ongoing adventure. There's always more to discover about our incredible universe.